This was an opportunistic site. We have some property owners who are, exceptionally open to the idea of testing things and allowed us access. We also know that this is a major source of contamination to the Christina River through the South Wilmington wetland, through this cut and into the river.
So the Sedimite technology is something that we have developed which allows us to bind up the pollutants in the sediments. And by binding it up, it stays in the sediments, and the organisms that we care about are not able to take up those pollutants.
So what we do in addition to the sedimite, the sedimite will sequester the PCBs, keep them out of the food chain. What we do in addition to that, by adding microorganisms that can degrade the PCBs, we're actually eliminating the PCBs in the process. So they're not only bound up to the carbon, they're also then rather rapidly degraded. So we're actually removing PCBs from the environment.
So we are kind of using two technologies together here. One is to bind up the pollutants, allowing it to be less available for these organisms, but in the long term we're also breaking it down and eliminating at least part of those pollutants over time.
And what happens is we take microbes that are already out there. The microbes we work with already exist in the environment. If we went in there, we'd find them. One's an anaerobe, and what it does is it clips chlorines off the PCB. Once those chlorines are removed, the aerobe that we add, these are the oxygen utilizing bacteria, will actually then break down, split the rings, and break down the PCB. So it's a two-step process that occurs concurrently. And what we do is we're taking these naturally occurring microbes and growing them up to very large numbers. If we didn't do anything and left this, decades from now, you'd see a reduction in PCBs by a process we call natural attenuation. But because the numbers of organisms are so low, it takes decades to see those PCBs disappear. All we're doing is taking those same microbes and increasing their numbers 5 orders of magnitude and putting them back in. And that speeds up the process so that we see, instead of results in decades, we see in months. So what we do is the sedimite is used just as it is, and we actually spray the microorganisms onto the sedimite. The sedimite absorbs water very easily, so we put the organisms in a salt buffer and just spray them on the pellets, and then they're distributed into the environment just like you would sedimite.
So it's a logical place to test this out. Who knows what the future will bring. Right now, we just want to make sure that it works. So this is a nice confined area for us to do that in.
We did a pilot study. We did a couple of pilot studies. Those were small-scale studies, one funded by the Department of Defense at Quantico. And this is the first in collaboration with Delaware. We are so happy to be able to do it at full scale, although this is a small area, but it's close to an acre. And this will really allow us to understand how it performs in the field at scale in a real site.
Of course, we have high expectations. We want to clean this up. Our WATAR goal is fishable, swimmable, and potable in the shortest time frame possible.
We should see results within 3 months. And it'll continue after that, but we should see results. We generally see results within a month if we go back that soon, but usually we spread it out.
These carbon application or carbon technologies, as well as some of the other things that we've tested through the WATAR program, are all meant to work on in specific locations, in specific environments, for specific contaminants. So again, when you put them all together in a combination, we can really achieve the goal quickly. So this isn't just a riverine thing. In the Mirror Lake project, we put it in a ponded area. This could work in stormwater ponds. This could be applied to other lakes, other rivers.
The results that we got in the last year, which looked at about 4 years post-treatment in Mirror Lake, the biggest impact that we are looking for was in the reductions of PCBs in the fish. And the resident fish showed big reductions that we were expecting, and we are so happy to see that play out at the scale of a 5-acre lake. So it worked great in Mirror Lake. In the Mirror Lake, we used just the sedimite with just the carbon, not the organisms, and that was effective in reducing the uptake of these pollutants in the fish.
The combined use of all these technologies and the advanced research that we've done over the past few years is going to allow us to work on a feasibility study for cleanup of the entire Christina River, at least our main source areas. We're going to kick off that initiative hopefully in September of this year, and bring a lot of stakeholders together to discuss the problem, discuss what some of our solutions could be, and to get other folks on board with helping to solve the problem that we have in the Christina. So this particular project is going to go a long way and give us another tool in the box to really tackle things at a much larger scale and enhance the results of our efforts.